Geostationary means that the satellite, that's the noun. We are describing what kind of satellite it is. So this satellite appears to be stationary, or you can say it is stationary. Geo means earth. So with respect to earth, so somebody is standing at a point on the earth, located on the earth, at a point located on earth. So this satellite appears to be stationary from a point located on the earth. Okay, so this is something like, so geostationary satellite orbits the earth at the same speed as the earth itself is rotating, and therefore it appears to always be in the same position relative to an observer on the planet. Okay, student, you can write down in your notebook simultaneously. Noted it down. Now here you can see in another figure which is showing the geostationary satellite, right? And the orbit is geostationary orbit. Okay? Yes, students? This is geostationary satellite and this is geostationary orbit. Done?
Yes, sir.
Now see, you have this another image of geostationary satellite. You can see that this is the so geostationary satellite is attracted by the earth gravitational pull. This Fg is the gravitational pull of the earth on the satellite. So we have radius of the earth and then altitude, sorry. So it's the radius of the earth plus altitude, that is height, and then gravitational force is equal to g m1 m2 divided by r square. So r is the radius of the orbit. Okay, so that's geostationary orbit. So I hope you have understood this concept, students. Yes, and see, like look at the how much is the distance, how far they are away from the earth. So they are it is around 22, so geostationary orbit, so means it is around 22,236 miles, so you can say 35,800 kilometers. Okay, above the equator, and it is its speed is equal to the Earth's rotation. This means that they continuously view the same area. So standing on the means these satellites continuously view the same area because they stay over a fixed spot on the surface. They provide constant vigil to identify and track severe weather conditions and environment hazards. Information from geostationary satellite is used for short-term forecasting, students, and also for tracking storm systems in real time. So So students, what are polar satellites now? So polar satellites, they are, you can also say them polar orbiting satellites. They circle the globe from North Pole to South Pole. Okay. So the second one, which is polar orbiting satellite, they circle the globe from North Pole to South Pole. Let us look at this figure. You can see even in this figure, if you look at this figure, you have this satellite as geostationary satellite and geostationary orbit, and this satellite as polar orbiting satellite or polar satellite, and this orbit is a polar orbit. Okay, because it is passing through the polar orbit. Okay, now see, this is in this figure, this is rotating, this earth is rotating in this direction, and so this satellite encircles the earth in, suppose, round about 100 minutes. So roughly 1.5 hours. So the earth is rotating and it will reach back. So see the location here. Here it was in this American map, and this is it was in East America. And look, this is your east, and it has reached the, so here it was west. So it has reached the west. So might be after 2 rotations. So this is 1, and then second time it was over here. So in strips it is means covering the whole earth. So polar orbit satellite will cover the whole earth, whereas geostationary satellite will be at it is showing you the position of a particular location only. Have you understood the difference between the two? Now the second difference, look at this polar orbit. This is a smaller one. You can see it is very near to the earth. Yes, can you see this thing? So polar satellites, low altitude, so the altitude is only around 500 to 800 kilometer. But what about this altitude? This we have found, means height from the surface of earth. For polar orbit it's only 500 to 800 kilometer. But what about geostationary? Yes, but the time period of geostationary, is 24 hours, right? Just like the time period of rotation of earth. But what is the time period for this satellite, polar orbiting satellite? 100 minutes. Next difference, it is polar geostationary, focus at a point, focus at a particular location. So showing you a particular location, and this polar orbiting satellites in this orbit, they show you whole earth, right? Now I was talking about this altitude, this height from the surface of earth, that is 35,800 kilometers. So see the difference, students. Here this height from the surface of earth, the polar satellite is 800 to 500 to 800 kilometers, and it is around 35,000. So how many times more? Around 50 times more is the altitude of the geostationary satellite. I hope you have understood. So time is also different for them. Now shall we move forward? Yes? Any doubts? Now let us calculate this 35,800, okay? What is the formula for time period of revolution for the satellite around Earth? That is equation 8.38. That is t square is equals to k into re plus h cube, right? That's also Kepler's law of periods, which tells that t square by the orbital radius is constant, right? That is what Kepler's law of period is. Now what is this value of k here? So k is equals to 4 pi square upon gme into re plus h whole cube, okay? So that's equation 8.38. Now what is the condition for geostationary satellite? I want its time period for one revolution same as the earth rotates on its axis, same time period. So that is 24 hours, we know, okay? So we need to find the value of h. So what will be h? So writing it in terms of re plus h whole cube will be equals to, so this GME will go that side, so that's T square into GME divided by this 4 pi square will come here, so 4 pi square. Okay, and further now RE plus H is equals to cube root of T square GME upon 4 pi square. Okay, so GME upon 4 pi square and cube root of it. Now this we have to find H, so take this RE, this is positive, so on that side it will be negative. Okay, so we know these variables, we know the value of T, that is 24 hours, so put it in seconds here. Okay, and then we know the value of G, 6.67 × 10⁻11. we know the mass of Earth, we know the which is we know the radius of Earth, right? So, and we know the value of pi. So put all these values, you will find that H is equals to 35800 kilometers. Okay, so that's how we get the altitude of the geostationary satellite. I hope this concept is clear, students. Shall we move forward? Yes?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. So very simple. Polar satellites passing through polar orbit and orbiting the whole Earth. Their time period of rotation is for the polar satellites, it's only around 1.5 hours. Okay, and for geostationary satellites, the time period is 24 hours. Okay. And their orbital radius, you can see, it's we have just calculated that the orbital radius are E plus H. This is your orbital radius and this is your altitude. That is for the geostationary satellites, the altitude is 35,800. Okay, you can read the theory from the book, students. And the figure is also given of the polar satellite. Next topic is weightlessness. So name itself is telling you weightless, so no weight. So weightlessness means no weight. What is your weight? No weight means weight is your mg, so no mg, right? How can it be possible that there is no mg? See, you have a spring balance, right? You weigh using spring balance, so you have tied a mass over here. Okay, so this spring balance, so we have a spring here which was in normal position, but as you tied this mass at the bottom, it will tell you the weight. Okay, so this spring will actually it will come down. So this hook will so this spring will be compressed here. So this pointer, it was over, suppose here, this pointer comes down at this position. So this pointer comes down here, and the spring is compressed. This spring is compressed. Okay. Right. So who is compressing this spring? This is the mass mg which is compressing this spring. And why it is compressing? Because see, it is tied up with another end, right? What happens if you don't tie it from other end? What happens? Can you imagine? Will this spring be stretched? Yes. You can do this experiment yourself also. See, you have a spring, okay, and like you have a spring, okay. Now you have means hold it from one hand, hold it, and then hold it means apply the force on this end from other hand. So stretch it. This is the direction of force. Stretch it from other hand. Okay. Yes, we can do it. So what will happen? This spring will be stretched. Am I right? Yes.
Yes, sir.
Now, this is a simple thing that you can do. Okay. Now, in second case, I am not holding this from hand. I am simply not holding by hand or with the wall. That's your choice. Not holding other end. And now again you are applying force. So this is free. This end is free to move. Okay. Not hold it. And you are now applying the force on this point. What will happen, students? Will the spring be stretched? Will the spring be stretched?
No, sir. No, sir.
Of course, no. So the thing is that if you apply force in this direction, then there will be linear motion, right? Translatory motion. So all of them will move in this direction, right? So all the particles. So that's translatory motion, linear motion. Okay. So this spring will not stretch. Is it okay? So here also, if I am not holding this spring balance, and this will let this spring balance also fall down. So it is falling down with acceleration due to gravity. Mass also falling down with acceleration due to gravity. So this mass will feel. So it is not showing you any balance over here. So if this is your mass tied over here. So this balance will not show any mass. It will remain here in the same position. So that's weightlessness. It is not showing any weight to the body. Okay. So that is the meaning of weightlessness. The spring is pulled down a little by the gravitational pull of the object, and in turn spring was also pulling it the object vertically upward. But now here the top end of the balance is no longer fixed. So when it is no longer fixed, both the ends of the spring as well as the object, all of them are moving with identical acceleration g, and the spring is not stretched and does not carry any upward force on the object, which is moving down with acceleration gravity g. So the reading recorded in the spring balance is 0, since the spring is not stretched at all. So this is the same thing that if you instead I was telling you this example of spring, you can tell here that this is the spring balance. Same thing. Okay. So this way also you can stretch this spring balance. So it is the same thing. So the spring balance will move here So here also this spring balance here, this instrument was fixed over here, but now the instrument is not fixed, so instrument is also moving downward with acceleration due to gravity. Okay, so the reading recorded in the spring balance is 0 since the spring is not stretched at all. If the objects were human being, then you will also not feel the weight. Why? Because there is no upward force on you, and thus the object is in free fall. So weightlessness means free fall. You are not feeling any weight upwards. Okay, so that's weightlessness, that this phenomena. So this phenomena is weightlessness. So weightlessness is the phenomena. It's the phenomena when the object is falling freely and it is weightless. So the object is weightless. During the free fall, object is weightless. Okay students, so write it down. During the free fall, object is weightless. And this phenomena is weightlessness. Okay. So what happens when the astronaut go into the space? Suppose they are in this satellite over here. So they are suppose in this geostationary satellite. So in a satellite around the Earth, every part and parcel of the satellite has an acceleration towards the center of the Earth, right? Yes. So its acceleration is towards the center of the Earth, centripetal acceleration. Yes. In the circular motion is due to centripetal force, and centripetal acceleration is towards the center of the Earth. So the value of this acceleration is g. Okay, the value of so this is so here the means in satellite acceleration centripetal acceleration is same as the acceleration due to gravity. Okay, so same is the case that the spring and the mass, so both are falling with the same acceleration due to gravity. So here also both are attracted towards the Earth, hence the centripetal acceleration is equals to the acceleration due to gravity. So that's the condition, and when this condition will be there, thus so in the satellite everything inside it is in the state of free fall. Okay, this is just as if we were falling from the falling towards the Earth from a certain height. Thus in a manned satellite, when there are people inside the satellite, they experience no gravity. So gravity for us, gravity means gravitational force, so they don't feel any gravitational force over here. So this just like this spring was not stretched, so your body is not feeling any upward force here. Okay, so gravity for us defines the vertical direction, and for these astronauts over here, for them there is no horizontal or vertical directions, and all the directions are same, and they even float in the satellite. You can see the pictures. Yes. So I hope you have understood this, students. So I have read this weightlessness from your book, and let me read some of the lines of the geostationary satellite also from the book, which is on page 197, second paragraph. It is known that electromagnetic waves. So now a little bit discussion about how this geostationary satellite is working. And so geostationary satellite is this is your equator, right? This is your equator. Okay. And the satellites, this geostationary satellite, this is your equator, and the plane of this equator, okay, so this is a circle, and the plane of this circle is your, this plane is equatorial plane. Okay, so this plane is your equatorial plane. Okay, so geostationary satellite orbits in this equatorial plane. So this is showing you equatorial plane. This is also showing you equatorial plane from the top. Okay, so sending them to the height of 35,000 kilometer needs very powerful rockets, right? So why we are spending so much of money to send the satellites in the geostationary orbit? So what's the advantage? See, we have let me show you one more figure. So you can see that this geostationary satellite, so you have a station over here, suppose. So this station is sending the signals in the form of electromagnetic waves. Okay, electromagnetic waves are what? All the waves means all the like radio waves. In the micro oven, the food is heated due to the waves. So microwaves. Then the waves coming from the sun, so micro radio waves, your FM, you see the means that radio with the help of these waves, and microwaves, and then you have the waves from the sun rays, that is infrared rays, and then you have visible rays, and then you have ultraviolet rays, and then you have X-rays. When you want to check whether any bone is fractured or not, or body checkup, you go for the X-ray. And then you have gamma rays also, which are very dangerous. Okay, so here wavelength is more, frequency is less. So as you move down here, so its wavelength is decreasing and frequency is increasing. Okay, so I am sending the waves from a station over here to this satellite, and then this satellite will enhance that signal and will send those signals in this much of area. So this much of the area is covered, like you are sending the radio signals, or your mobile phones. That's how mobile phones work. So from the station, the signals that you are talking on the phone, so here is the phone and another person is over here, so that's how they are sent to this. Okay, and suppose some person is over here, so then from tower to tower, so from this tower to the signal is transmitted, might be from this tower to this tower here, and then from this tower to this tower, then it will again send back. So I hope you have understood how this how it functions, right? Yes. So electromagnetic waves above a certain frequency are not reflected from ionosphere. So we have ionosphere here. Okay, so your radio waves these radio waves, they see earlier on, means like 200 years ago, 100 years ago, there were no satellite 100 years ago, but still we were able to listen to the radios. So why? Because this is ionosphere, students. Okay, so we have ionosphere, different layers of earth you have seen. So ionosphere is a top layer sort of. So radio waves, they have low frequency. So low frequency waves are reflected by the ionosphere. They don't need we don't need to send them to satellite. So radio waves reflected from ionosphere only, okay, and come back to earth. Is this clear, students? So the radio waves for the radio broadcast, which are of the frequency 2 megahertz to 10 megahertz. We have one whole chapter, electromagnetic waves, which is chapter number 8 in class 12. Okay. So, and this thing is over there, like the spectrum. I have written it over here. And so these radio waves are reflected from the ionosphere, which are below the critical frequency. Now if you increase the frequency, here the frequency is increased, okay. So as you are moving down, frequency, as you move down, frequency increases, and wavelength decreases, okay. So as you move down, this sequence, wavelength is increasing. So here this is below the critical frequency. So we call the frequency critical frequency till the ionosphere, till the waves are reflected back from the ionosphere. So that means the frequency, that maximum frequency is your critical frequency. So beyond, if the frequency is greater than critical frequency, then waves will go beyond ionosphere, okay. They will go beyond the ionosphere, and then for them we have satellites, okay. So radio waves, ionosphere is okay to reflect them, but for next means for certain radio waves, so even radio waves are of many types, students, like okay. So the radio wave still it is the frequency, the critical frequency. So everything depends on critical frequency. And then you have your mobile signals. So mobile signals also. So mobile signals have greater frequency. So their frequency is greater than radio waves, okay, and they will not be reflected by ionosphere. So they will go to the satellite. So we have satellite phones. I think you have heard. We have satellite phones also. So so the main thing is that they are reflected back by the ionosphere. But thus the radio waves broadcast from the antenna can be received at point far away where the direct wave failed to reach on the account of curvature of earth. So directly the waves fail to reach radio waves, but from ionosphere they are reflected back and they are used for communication. Now waves used in the television broadcast and other forms of communication have higher frequency. So for TV broadcasting, like, yes, all of you have dish antenna at your home. So for television broadcasting and other form of communication, we need much higher frequency, and those higher frequencies will not be reflected by the ionosphere. They go beyond the ionosphere, okay. And geostationary satellite appearing fixed above the broadcasting station can, however, receive these signals and broadcast them back to the wide area on earth. The INSET group of satellites sent up by India are one such group of geostationary satellites. Okay students, so I hope you have understood it. Okay, thank you so much.